Okay, good morning. Let's get started. I don't know if more people will be coming, but maybe once one closes the door, you usually come. I've noticed it's the last week of the lecture period. Yes, I wasn't aware of that. I wanted to show you a bit more, but now we have to sort of stop somewhere in the middle. We can continue. We can think, of course, about if there's interest and if we get more people from the other side, we can continue in the next term or something like this. But for now, what I wanted to do to close the whole stuff is to talk a bit more about trajectory inference or pseudotime. So given that we have some curved manifold, which is somehow elongated, we want to bring the cells in this manifold in order, depending how far off they are. And we've used this pseudotime the last, no, not the last lecture, but in the lecture before, in order to regress the gene expression onto it. So we sort of took it, but we didn't really discuss about where we get it from, and this is what I want to do now. And there is different ways to do it, and the two more popular is going along principal curves and going along diffusion maps. And I thought that I start off briefly showing how the principal curves work. I actually had planned to go into more detail for this next week, but next week is already end of term. Let's see what we do with this. But so we'll have a brief look at that to get a rough idea how it works, and then we switch over to diffusion time, because the diffusion time, the diffusion pseudotime has very neat mathematics, and that's quite nice to look at. So I've prepared 2 lectures. So you might have noticed by now I'm starting to hope that I can do this whole thing maybe into a little kind of larger written tutorial or a mini textbook or whatsoever. That's why I now put a bit more effort into it. So let's start here with the principal curves. And for the principal curves, we need some kind of example data. And what I use as example data for our first step is this here. Before, we've already worked in some 30-dimensional principal component space. And there we had to be careful that we kept in mind that what we see on our 2D plot are not the real distances, but just the impression of a UMAP projection, how it best shows the real distances. And that would further complicate our attempt to follow what our principal curve algorithm is doing. So this time the 2D space is the real space with the real distances, so I generate my data in the 2D. And to do this, I used a spline. You might know these splines from vector graphics drawing programs. You have a couple of points like these here, which, as you can see, I have just completely manually decided and played with them until I liked my curve. And when I use this spline methodology to make a curve through them. Now this stupid thing, it doesn't work again. Okay, let's try. So here you see I have now a smooth curve going through it. Unfortunately, we won't have the time to talk about splines, how they work in detail. So for now, you will just have to see a little bit of what's happening here. Maybe the very rough explanation how splines work is here. We're using some kind of splines called B-splines. And before I have to explain the word spline. Spline is a mathematical term, but of course, originally it was a term from mechanics, from technical drafting. If you're a technical draftsman in the olden times before computers and you drew a technical drawing on a big piece of paper, then of course you had your rulers and your protractors and made straight lines, but sometimes you have to use a curved line. And these curved lines, and for these curved lines, you had a Kurvenlineal in German or spline in English. That's lineal. Let's look if we see a picture of this. Yes, it's simply a piece of stiff rubber with some kind of thing which you can bend into arbitrary shapes in order to make smooth curved drawings. Feels funny if you have this in your hand. In English, it's called a spline, and when the computers came up with stuff, the question came, how do you best parameterize these things? And there's two approaches. One is called Bézier splines, named after an engineer for Renault, who wanted to draw, well, automobile chassis. The others are these B-splines. And the fundamental idea of a B-spline is, where's this plot of a B-spline basis? Picture. Here is a picture of a B-spline basis. Is you have a number of third-degree polynomials. So this, for example, is you see this thing is internally divided into different parts of knots. So, for example, here's a knot, here's the next knot, here's the third knot. So wherever something starts, it goes to zero or it comes out of zero, there's a knot. And each of these individual curves, they always go over two segments. So from one knot, switching over to the next knot. And there are three polynomials of the third degree with the following properties. Each polynomial is non-zero only over a limited area, and afterwards it's sort of forced to be zero. So we always say here it's a polynomial, and after the knot it's forced to be zero by sort of a case-wise definition. And as you can see, they sit there, and they are defined such that if I take any point t here, any point on the x-axis, and I add up the y values of all the curves, I get 1. So each point here is a partition of a 1, and they always add up to 1. And there is a little construction, which is discussed at length here in this Wikipedia page, where you can see how you can write these in a how you can find these splines with this recursive formula here by just starting with triangles, and when you add up always two neighboring triangles, etc. What then happens is, what you now next do is, where was this picture? If you have here your points, in order to get your spline, you always move along all these points here, from here to here. So my curve from 0 to 1 is split 0 to 1 here, 0 to 1 here. In each curve point, for example, here the curve point up to 1/3 of the whole length of the curve is 1/3 of this, is the point 1/3 along this line, plus the point 1/3 along this line, plus this and this and this, where the different points are weighted according to these curves. So at the beginning of a curve, you mainly take weight from the early lines. At the end of a point, you take weights from the late lines. And because the weights add up to 1, if you take always each of these points and multiply them, you get a smooth curve. And how this works here, you can, maybe I quickly show it to you because it's such a nice little piece of thing. So here I have my C-bind, and here I now have my spline basis, where I use this B-spline function from R. And this B-spline function, this spline basis, it simply looks like this. As you can see, it is a matrix with 10 columns, because I have 10 such curves here. And if I plot these 10 curves, matplot, type equals L, and you see here how this is with curves that I have. And so, for example, if I now, and what I now do is I have told it that I want to have this area here from 0 to 1,000, I want this split into 1,000 pieces. And so if I now take the value of the spline basis at, say, 100, which is 0.1 along the curve, 100, then you get these numbers here, which have weight only on the first 4, but not on the last. They add up to 1. And what I now do is I take these lines here, and I calculate which point is 10% the length between that and that, which percent is 10%. So I use this point here, this point, this point, this point, this point, these points. And I take the average between these all points, averaging according to these things. And as these curves are smooth, and I smoothly move my points here from the left point to the next point, you can imagine that I get a smooth curve. And that's the way how you generalize this spline idea from having this funny draftsman's physical tool into something on the computer. What I now did is I just took me 1000 value, here's along this line from 0 to 1. And these are my pseudotypes of my cells. And now I imagine that these cells sit on this curve. So I use here with X, I look up the points at this position. And now you see they all sit here in some more or less uniform thing. And now I add just some random noise with 0.1 to the right, left, and to the top down. And if I do this, then I get this here. No? Yeah. And of course, I can add to this the remaining, the original line, and you see this is a way how we can get an example data. Now, of course, our real single cell data might be look much more complicated, the way how it curves through this 2D space, and we should keep this in mind. So we are making the job easy for our principal curve elements, but of course, you should start with something easy to understand and then we go further. So what I now want, I want to essentially be able to project each gray point onto the blue line, and then put a scale on the blue line that I say this here is 0, this here is 1, and the points in between also have numbers along the curve, such that the curvilinear distance is sort of slowly indexing from 0 to 1. And in this case, every color, every point here gets a number. This point might get the number 0.3, because if I project it here, it has 1/3 of the length of the curve. The length of the curve along this thing is, of course, defined by the curve integral. If you don't know how that works, well, you can imagine. So, and our job to do this is, of course, projecting onto the curve is easy. We just find the point on the curve which has the shortest distance to the data point. But, actually it's not that easy, but we will skip over how to do that for lack of time. But we first need to find the actual curve. And this is where this principal curve package comes in. And if I now simply call the principal curve function, X, it produces me here this PRC object, which, as you can see, has here a lot of output. It gives you first here an object S. That's the actual curve, where all these here are the coordinates of 1000 curve points. And it's the projections of the 1000 individual points that I have here. And here it tells me the projection numbers, so the pseudo-time of each point, and so on. Now let's plot here these 1000 curve points and add them to our plot. And then what we now see is this blue dashed line is the line we put in, and the orange, the brown line is the principal curve we got out. And as you see, it's not that great. So let's first see what this principal curve algorithm actually does. And as I said, I wanted to do is to make the principal curves a bit short and have more time for diffusion time. So let's just quickly skip about what this principal curve algorithm does. What it does is it starts with some random guess of a curve. Let's say this brown curve is our current random guess. When we take each data point and project it onto the curve, and the projection we do by finding that point on the curve which is closest to it. So we take our point xk and go through the whole curve and always calculate the distance between the point and the curve, find the curve point with the lowest, and because the curve is parametrized, you see my curve is a function of this unit interval from 0 to 1, to my vector space, in my case r squared, or in general Rn. So if I let t run from 0 to 1, I get all these points, and ask which of these points is closest and what is the corresponding t. And this t point that gives me the minimal point here is this the pseudo-time coordinate of this point x.
How is this curve kind of parameterized?
That's what we come to next. Let's at the moment assume we parameterize it somehow. So the next thing, what we now, as you can see here within the data point, what we get back, our curve is parameterized as this hat PRC $S as simply at 1,000 points, and we make it as a polygon line. So between each 2 points, we make a straight. Of course, in reality, it should be curved, but we approximate it that way. This also makes our projection easy because we know how to project a point to a straight line, namely by just projecting the vectors onto each other. And in that way, we can easily find this. Now, these points, of course, this list has to be generated by coming out of some parameterization. And R uses 2 ways. This sprint curve thing uses 2 ways. As its default method is to use splines, exactly the same way how I made my original calculation. So it tries to find a list of points here. But it only tries to find 5 points, which is why I can already tell you how I will solve this issue here that this curve doesn't fit properly. I tell it don't try to find 5 points, try to find 10 points. I'm just saying allow yourself 10 degrees of freedom, and then it looks much better. Now, the part which I haven't been able to show you is this spline regression. Once you have these splines, you can try to find these points. Or what you can also do is, so spline regression, B-splines can be used in 2 ways. One way is what I've just shown you here on this thing, where we said the B-splines, we use them to define a curve. Another thing is, so this is something we can use if we have a curve in n-dimensional space. But now let's imagine we have an old-fashioned one-dimensional function, simply a function of y coordinates as a function of x coordinates. So imagine you have some arbitrary function y of x which somehow lies in here. Then you can try to approximate this function by using these basis points, because if I go back here to my basis splines, to my spline basis, where is my spline basis? Here it is. You remember we had all these points here. And now what I can now do is I can take, for example, say I want to have 3, 4, 5, 6, 7, 8, 9, 10. What I have done now is I just took out the first column of my spline matrix. I can also say, and if I plot this, so if I can plot this, then of course I get the first. I can now say I want a mixture of a little bit of a first, a bit more of a second, a bit more of a third, and what is left now, 0.4, 0.7, 0.9, and 0.1 here. And now we get a rather complicated curve. Maybe we have something more here. And as you can imagine, what we can now do, if we have a complicatedly shaped curve and we want to parameterize this, one possibility is to use the local regression that we discussed 2 weeks ago. The other possibility is to find parameters, to find a set of 10 values here, such that the resulting curve here gets as close as possible to our real curve. So, for example, if my real curve is plot t, x, x1, so this as the x coordinate is just the x coordinates of my curve. And I want to regress this onto splines. What I can now do is that I say LM, I want to regress x, 1 onto this spline basis. And what I now do is I take the spline basis, but here the spline basis is for random values from 0 to, is for values from 0 to 1. You see here in my spline basis, if I go up again at the spline basis, each one here corresponds to a t-value to the next t-value and so on. But in my data matrix here, my t-values were not ordered. So I have to bring the spline basis. So for each t value, I want the corresponding spline basis. And I do this by simply saying B splines, B splines, and now I take, instead of here a uniform sequence from 0 to 1, I take my actual t values, and now I say df is 10, and I get here this kind of thing, which is a matrix, and now I can simply say Lm and what it has now done is, or let's say intercept is 2, true, and it looks the same as before, and tell R that I don't want an extra intercept. And what it now gives me is here coefficients, and if I take these coefficients, OF fit, and multiply them again with my spline basis, this time with my random sequence 0 to 1, or with, let's do it like this here with my, if I multiply this again with my splines here, then I get y values, and this y values, lines, t, comma, no, not lines because they are not in order, points, comma, cal is red. And as you see, we've got a spline. So this is called spline regression, where you regress onto this. And the magic thing that happens here is this thing that I put into my linear model. That is just a big matrix which we want to fit onto. And all that R has to do is to do a Gaussian elimination on this big matrix, and it gets these spline coefficients. I could probably prepare a whole lecture on explaining what exactly is happening there, because on one hand it's deceptively simple, but on the other hand one needs a while to understand how simple it is. But this is what print curve now does internally. This is how it gets the x and y coordinates of our splines. And this is also why we didn't get, why we got a bad one if we took only 5 values, because if I give this thing here only 5 degrees of freedoms, when it uses, instead of 10 curves here, it uses only 5. And well, in that case, it worked still quite well, but you can imagine that it then has problems with tight curves. Yeah?
So at the beginning, you mentioned that instead of using all data points, they kind of approximate data by essentially coordinates first, and then they do the spline regression.
I do coordinates first.
So you mentioned that they use kind of not all data points, but like essentially connected points.
No, that was just to report it back to us. It gives us 1,000 elements on the curve.
Okay.
What it internally does, yes. Now, if print curves wants to do this internally, what we've just done, the missing part you see here in the linear model, we regressed the splines. We used the pseudotime, but of course, in the beginning, we don't have the pseudotime yet. And this is why we need to do this iterative procedure, where we first take one random curve, for example, just a horizontal line, and we project each point onto this line, and that gives us a preliminary pseudotime. Then we can do a regression, and then we get a better curve, and then we can regress, project again to get better pseudotime, and so on. But you can already see how this can work badly. For example, if your curve somehow is curving too much, it could be that you end up in a local minimum, and it never really managed to find it around. So for example, if you have some kind of U-shaped thing, and you give this to the print curve algorithm, it often doesn't find the U. And so this is what I've written up here as the way how this thing works. It projects, takes an initial guess, when it uses this initial curve to find a t for each function, and then it regresses the new curve when it regresses the data points onto their t's in order to get a new curve. And this regression can either be done using spline regression, as I've just quickly shown you, or using local regression, exactly the way how we did it 2 weeks ago. And here you see how this looks like a spline regression. If I tell him to make a spline basis with 10 curves instead of 5 basis curves. And here you see how it looks like if I tell him to use local regression. And in the local regression, you might remember this nearest neighbor parameter that we had, where we said we make the kernel always wide enough that 20% of all the data points are under the kernel. Here, this is 15%, is what I used here. Because again, when I started it with default parameters, it wasn't able to make tight enough bends to follow the whole curve, and that was because the default value of f, I couldn't find out what it is, but obviously it was too large. So, what you often have in practice, however, is branch structures like this one here. You see, I made a second curve, and then I put the two curves on top of each other, and now each point either lies on this curve or on that curve. And initially the curves lie together, and then they differentiate. I did this by just making the first 7 knots are the same between both curves, and the last 4 knots are different. And in that manner, I now get this thing. I want to put a curve through that. And if I now did this with just the principal curve thing, what would happen is that it just makes a curve like this, which is not what we want. We want the curve to branch. And there's one R package called Slingshot, which tries to do something like this. It tries to fit 2 curves. One curve which follows one branch, and one curve which follows the other branch. And I want to quickly show you how this works. So Slingshot, by default, if I just take the Slingshot package as it is, and I give the Slingshot my data x, then it will just produce exactly the same as the principal curve function. So you see here the dotted blue line is what printcurve gave us, and the green line is what Slingshot gave us, and it does the same thing. As it should, because we gave it the same parameters, namely df10, and because Slingshot internally uses principal curve. Now, if you have a branch structure, what Slingshot wants you to do is to first help it find out which cell belongs to which branch. And to this end, you're supposed to do a clustering. So I do my usual Leiden clustering, as we've done now often. And so my Leiden clustering, which time gives me this clustering here. And now we can say, okay, one branch is probably 6, 8, 3, 2, 1, 11, 4, 10, 7, 9, 5, and 13. And the other goes here up to 9 and then goes on to 12. If we call Slingshot with this x here and with this Leiden membership, so you remember that was this vector that tells us for each point the number of a cluster it is in. And then Slingshot produces a tree, this one here. So each number here is a cluster, and as you can see here exactly our clustering structure from 6 to 5, and then we either branch to 13 or to 9 and 12. Either to 13 or to 9 and 12. It deviates a little bit. You see it takes here 5. If I look at that, I would have said the correct branching is 7, 9, 12. But it does here 7, 5, 9, 12. So it seems to go a little detour, which we don't really see here because it didn't manage to take this bend anyway. So where does this tree come from? We take our clusters, we see which clusters share a lot of neighbors, so we make a graph where each cluster is one node, and then we draw an edge whenever the graphs have a lot of neighbors. You remember I once gave you a homework where I said, let's try to do this, draw such a graph. I think we never discussed about it. I also tried it myself, and I always got more edges than I wanted. This thing must have some clever way, and I haven't looked up yet how it does that. But still, we would expect that it gets some kind of triangle here. 7, 5, 9, you see they're all clearly neighbor to each other. But in this thing here, 7, 5, 9, this edge here from 9 to 7 is missing. This is why it took the graph, and then it calculated something called the maximum spanning tree. maximum spanning tree. This is a standard classical graph algorithm. Sorry, the minimum spanning tree, where you have a graph here and you try to find a tree in the graph which is minimal. Tree in graph theory means a graph without cycles. So where everything is branching, but the two branches never close back to each other. Minimum tree means a tree which touches all corners, all nodes, and is minimal in the number of edges. But here in the length of the edges, but in our case we have only the number of edges. I.e., we kick out edges and try to gain a tree by kicking out as few edges as possible. In that way we come to this thing. And there's an efficient way to find the minimum spanning tree, which is described here. I've forgotten how it works, but it's one of the sort of the classics of graph theory. If you then learn to go into a graph theory lecture, this MST algorithm is usually the first thing you learn. So, and with this minimum spanning tree, we now get this thing, where our thing now says, okay, obviously I have two branches. One goes from 6 to 13 and the other goes from 6 to 12. And in order to get this, all that it has to do is that it first runs principal curve on all cells except for those in 13, and then it runs principal curve on all cells except for these in 12 and 9, and then it gets these two curves. It makes a slight little improvement here in terms of the cluster 5, which is joined by both of them. There it tries to weight the cells and say the cell should get more weight for one curve or more weight in the other curve. And it always makes its curve, and then it checks, is this point closer to one curve or to the other curve? And then in the next iteration, it downweights the cell on those when making the curve where the cell is further. So for example, this cell here will not have full weight when making this curve. But in the end, it uses print curve. These principal curve algorithms have some way of doing weighting, which you can imagine is easily done because we use spline regression and local regression, where it's easy to give each point a weight. And so we can downweight points where we have decided they are most likely more belonging to the other curve. And if we now look at what Slingshot has given us here, let's go up to here and have a look at, where is it? We can now have a look here. Slingshot is again one of these annoying objects with lots of parts which we can't quite fight, but like Sura. But here in essays, I have here found a table with the weights, which I somehow don't manage to access. Here, it gives us for each cell the weight, how much they think it's one or in the other branch. What it also gives us is for each cell a pseudotime, which tells us what pseudotime value this cell has in its respective branch. And if it doesn't appear, if it has weight 0 in a branch because it's in the other cluster, we don't have a thing. So I can plot these two curves. I can plot these two things, and you see this is the first lineage here, where the pseudotime runs from here to here, from 0 to 6. And these ones are gray, and the other one looks like that. And you see these cells here, they appear in both pseudotimes, while the others, they are kicked out because they are probably outside this thing. So this is one way of getting a pseudotime. And as you can see here, where do we have it? And seems to work reasonably well. Now I tried this on a bit of more data, and actually the first problem I had is in my initial try I made this branch much shorter. It only went up to here, and this part was missing. And then somehow the clustering worked the way that that the graph didn't become nice. Or I had the issue that here, if I make it a bit thicker here, when I get two clusters next to each other, and then we get bulges here. And then it starts making, so for example, if this cluster here would be broken up longitudinal, that you have a cluster 2A on top and a cluster 2B at the bottom, when in the curve, in the tree, it will then say, okay, there is here another one and connect it like this. And we have here an extra loop in the MST, one of these two edges kick out, and then it thinks, oh, I have to fit a third branch which goes here. So what I've learned from that, I wouldn't trust the slingshot's automatic calculation of this tree. You're probably better off twiddling with the clustering until the tree looks good, or maybe find your spanning, not take the minimum spanning tree, but draw your tree manually, like tell it along which clusters the thing should go. The other issue that you've already seen is by default, the slingshot algorithm uses the defaults of principal curve, and we've already seen they are not good. They are too stiff, at least for my data. How do we know that they are not too stiff for real data? Here it's immediately obvious, because we can look at this thing and say, sure, this is not a this is not a proper thing, but this is because my data lives in 2D. If my data lives in 20 principal component definition, it's really hard to see how to see whether your fit is good or not. In my opinion, and that's something I would have liked to explore a bit more with time, we need some diagnostics. For example, here an obvious diagnostics which would show us is noticing that all these points here have quite some distance to the curve. There is no points with distance 0 or nearly 0. So obviously the curve doesn't go through the middle, but somewhere by the side. And maybe these are things one should use a bit to check all this out a bit. In practice, the whole thing happens a bit that I think most practitioners will just take this slingshot, run it with default parameters, and are happy with what you get out. But maybe this is not as appropriate. And I told you already 2 weeks ago, I had this data set of hours where I once run slingshot and once run this diffusion period time on it, and I got completely different results. And one made it in the paper and the other didn't. So yes, we did exactly the same thing 3 years ago when we analyzed this, just running it by default and not asking further questions, but we should have done that. So this is what I wanted to say about using principal curves and about using slingshots. Are there questions about that?
What do you think about the degrees of union, like the cell state space? How kind of like strong curves could there be or not? Like, what is possible reality?
This is a good question. I'm wondering how to best do this. The problem starts with that it's not so easy to even draw your principal curve into a UMAP space, because UMAP is not exactly a linear mapping. So if you have a PCA if you have a curve in a high dimensional space, you can ask UMAP to map it down to 2D, but that doesn't work that quietly. And how to actually figure out how curved it is, I wonder, but maybe one should. And it's actually something I want to look a bit deeper now in the next months, also research-wise. Which reminds me, I wanted to say, if any of you know anybody who wants to do a summer practical or a master thesis or is looking for a PhD position, I'm looking for people. And yeah, exactly, asking these kinds of questions might be worthwhile, because in our group we're now working so much with trajectories and pseudotimes, and the more I think about it, especially now that I've spent quite some time preparing this lecture, the more I have a feeling maybe somebody should revisit the basics. But also for people who are more interested in going into real biology, we have stuff on methylation, stuff on denoising, on autoencoders. So there's plenty of work to do. I mean, you're now only a few people sitting here, but maybe you know somebody. Or you're interested yourself. So, what was the other thing I wanted to show you? So here's the references. I've decided to finally start adding references. The original idea of principal curves is by Hastie and Stützle, and it's from '89. So as you can see, this is an old idea stemming back from long before anybody talked about single cell. He had more machine learning questions in mind. And they also published this data, this principal curve package that we've just used. I think Hasty has written it. So Hasty is now one of these gray eminences of statistics, like a very retired professor who has known it all. While this year, I think it might be his PhD thesis or something like this. So this is what now, 40 years ago. 35 something years ago. The idea to use Slingshot has been written by people out from the Purdom and Dudois group. They, as I said, they used this Slingshot and came up with this idea of using this iterated reweighting in order to get the branches. And here it's published here. So the other thing. Nearly. You see, it has here fitted two curves. They sit more or less on top of each other, but not exactly.
So, like the T value of each curve goes very close to each other.
Exactly. Yeah. We do this. It's of course what we want, because biologically we imagine that this might be some kind of stem cell which then amplifies and so on, and here it makes a cell fate decision and either continues to become differentiated cell type A or differentiated cell type B. And one biologically interesting question is, when do these 2 points actually branch? Because people always have this idea that that at some point the cell decides and then it goes either way. And people imagine the manifold a bit like I've made it here for my example, that there's one clear branching point where we start to separate. Now, Lars Welten, who used to be at working here as a PhD student I think he was working with Trump or with Lars Steinmetz. Now he has his own group in Barcelona. He made this together with people from the Trump lab. They made this nice paper a couple of years ago for homeotopoiesis, where they put this into question, and they had the feeling that the manifold looks much more like this here, like some kind of fan, where you start off maybe early and then it branches out like this. And there's quite a long part where the cell can sort of walk around, and maybe it seems to go towards one direction, but then it changes and goes to the other direction. So where sort of cell fate is half decided, where you can say this cell looks more like it's going to this or that, but the decision isn't final yet. So the decision doesn't seem to happen really at one point, but it seems to happen that the difference between cells on the two different paths becomes larger and larger, but still not so large that the cell couldn't somehow be pushed to the other side over. Like if you would imagine this like a Waddington landscape, it wouldn't be like a railroad track where you have one switch where things switch, but rather like a kind of trough which becomes wider and wider, and the ball can go back to the left and to the right in this wide trough, and only at the end comes something in the middle where it needs to decide. So maybe if I draw this as a Waddington landscape and this is downwards, and I would say, okay, here the ball can go either way, can be bumped by random stochasticity rather to the left and to the right, and it happens rather late when there's actually no way back anymore. And this is of course something which we can't project well with this kind of curve. So this idea of using pseudotime curves is probably not exactly the final say in this whole matter.
Why would it make biological sense that we have this branching that happens over a long time, kind of like where cells could still
imagine, because if you have a cell fate decision, you probably need to lock it in something. That's at least how I would imagine it. That such a decision is usually in biology, you lock decisions in by feedback loops. You know, with positive feedback loops. You know, something is some transcription factor stimulates its own transcription and so improves with more. And now in the beginning, you might have two transcription factors, which with one causing either one trajectory and the other causing the other decisions. And at the beginning, they sort of compete. They both try to get their positive feedback loop locked in and have negative feedback on the other. Let's imagine that each transcription factor stimulates its own expression and inhibits the other ones. And at the beginning, this is sort of balanced that both can happen, and then external stimuli, which aim to push the cell into one or the other fate, might give a little extra boost to one or the other, and so they struggle over quite some time until finally one wins out. And that's how I imagine how this happens. And that you want this decision to take a while in order for the cell to pick up stimuli from the environment and integrate up potential arguments for why you would rather want to become cell type A or cell type B. After all, this is a decision you have to pick depending on what's needed, which you learn from the environment, and for this you have to collect signaling from the outside for a while. And so I imagine this as some kind of balance where the cell puts evidence for we rather need cell type A or cell type B for a while, and the balance sort of always swings a bit up and down until at some point one evidence is so overwhelming that the balance falls down on one side, and then you've locked in. That would be my idea, and but this is exactly the kind of things which you don't see if you look at such plots. And so, yep, this is something that I always think that we should put more research into how we do that, because maybe revisiting the stuff that Lars started 5 years ago. But let's imagine we stick for now with this quasi one-dimensional idea where each cell is just projected to a point in pseudotime, and we only ask about which branch it is on, because notice we are also doing something else. We assume that all the cells with the same pseudotime on the same branch are somehow the same, which they probably aren't. So we simplify our whole state space to a branched quasi one-dimensional entity. But for now, it's probably a good start to bring ourselves at least into some order. That's what we've seen 2 weeks ago when we did this regression onto a pseudotime. It allows us to make easy to interpret with plots of gene expression along pseudotime. In order to do this, in my experience with principal curve, it's elegant and simple, but it has tendencies to have some issues with discovering branchings correctly, especially if a branching is complicated, if it's not as readily apparent from the clustering as it is here. The diffusion map concept has a much more unbiased way of finding branches, and that's why I want to show you this one as well. So here we have a diffusion distances, and I use again the same example data. And here you have our example data. I already used colors so that you indicate which ones are black, which one are one branch and which are the other branch. Of course, our pseudotime algorithm won't see that. That's just for us. While our algorithm has by itself to find out whether it's on the red or on the black branch. And the thing that we do in the pseudotime algorithm is when we go back to our neighborhood graph that we talked about when we discussed line clustering. You'll remember in the neighborhood graph, we connect each cell. Each cell is a node in the graph, and we draw an edge from each cell to its 20 nearest neighbors. And we make the graph undirected by forgetting about which direction the edge has pointed. And now we use this graph and we introduce something called a random walk. A random walk means we have some object, depending on who tells the stories. In some books, it's called a drunkard, because the guy is drunk and he doesn't know which direction he's walking, so he stands there and he randomly makes a step forward or backward or to the right or to the left. And the question which is always is, we have this guy who every second makes a step in some random direction. How far will he have gone from his initial point after time t? And it turns out that the distance our drunkard can travel in time t is proportional to the square root of t. Because, of course, you can always come back and forward and so on. And you can easily simulate it if you're now wondering why the square root. Remember the Galton board. Everybody knows where is it Galton or Galton? This thing here. You know this thing? The Galton board. It's used to demonstrate the binomial distribution. So you have these little pebbles or little mini balls on top, and they go down here through the thing in the center, and then they hit on this pin. And because they hit on the pin, they can either randomly go to the left or to the right. And we hit on this pin, and I guess push to the left or to the right. And so the maximum they can go is that they always push to the left, and then they end up here. And obviously what you get is a binomial distribution, and it's obviously the same case as our drunkard. The drunkard also randomly walks either to the left or to the right. Yes, exactly. So our drunkard randomly goes to the left or the right. And now I ask, how far will he have gone from the starting point after t steps? And the answer is, it's normally distributed. The probability of having walked, if each step is of being x meters from the starting point after t steps is exactly a normal distribution, a standard normal distribution accordingly. And the width of a standard normal distribution is square root of t. Why is it square root of t? Because we add up t steps, so our total distance that we have traveled is the sum of these t steps. Each step has a fixed variance, so the variance of the total number of steps, or the sum of steps, has n times that variance, so the standard deviation is the square root of n, and that's how you get there. So this is called the drunkard's walk, or the random walk, and so far I always imagined I put it here on my two-dimensional floor, so I can make steps backwards, forward, right, left, but I can also do this on a graph. I put my drunkard on a random cell and tell him each step, you step to one random neighboring cell, and then you step another random neighboring cell. And now the guy walks around, and that's what we call a random walk on the graph. And we can now ask questions like, if our drunkard starts at cell I, what is the probability that after t steps he arrives at cell j? And we call this a Markov chain, because a Markov chain is a probability process where in every step you can make your decision on what your next step will be doesn't depend on your earlier steps. And that's what our drunkard does. He doesn't have a memory. We also call these random walk processes diffusion processes, because a more important practical aspect of our random walk is Brownian motion. Imagine I would have a piece of tissue paper and I put a molecule of blue ink in the middle. And this molecule makes a Brownian motion walking from fiber to fiber. And if I put lots of blue ink, I can see the distribution, because I can see where each of them is, and the distribution does have the shape of a Gaussian. And the size of our ink spot is it goes with the square root of the time that we wait. This is why we call this also a diffusion process, even though mathematicians like to distinguish and say random walk if it's discrete steps, and diffusion if it's a continuous process. So, and what I will now do for my first thing is I will define such a diffusion process where the drunkard is put on a cell and moves to the next cell. and the probability that he goes to a neighboring cell will depend on the distance. The further away the cell, the less likely he goes there. So each hop happens with a probability, and this probability gets here a Gaussian kernel. I say the probability of going from cell I to cell J depends on a Gaussian with a fixed sigma, so that you can imagine if the distance is something like 1 sigma, it's quite probable that it takes it, but if the distance is something like 3 sigma, then the probability of getting there is less than 1%, or less, or even further down. The size of a kernel, we'll see this later. For now, we just take something random, and we have here, so we say we define what I call the kernel matrix, and the kernel matrix just contains these values here, d to the iy squared over sigma squared. Notice that most elements in this, so this kernel matrix is a matrix, an n by n matrix, which tells us where the element ij is the distance from I to j squared divided by sigma squared minus in front and exponentiated. Obviously, for all pairs of cells for which the distance is much larger than sigma, the value is nearly 0. So this value is sort of this matrix is nearly sparse. It has lots of very small values, which is something we want to keep in mind, because if we want to do this in practice, we better replace all these nearly 0 value by actual 0 values, so we save computation time. But for now, for this initial thing, I want to split up these two issues of using the actual sparse and so. So for now, I just use the full dense matrix. And this full dense matrix, here I have calculated it. You see, I put sigma to 0.3. And now I take my matrix X with all the things. And if I say dist X, when it calculates the distance from every row to every other row. So that's a function in R. But it gives us this in a strange format. So usually I have to say S matrix dist X. So remember, X has 2 columns or 2 coordinates and 1 row for each cell. And we have 1,000 cells, and now I have here a matrix of 1,000 by 1,000, and it tells us here always the distance of each cell to the other, which is just the Euclidean distance between the ith and the jth row in our original data matrix X. And obviously I can make this distance now squared, divided by my sigma square. Let's say sigma is 0.3. Put a minus in front and exponentiate it. This is the Gaussian kernel. And call this the Gaussian kernel matrix, Km, for kernel matrix. In my text, I've now got a bit the inconsistency that I use slightly different letters in the code and in the formula. So in the formula, I call it K, and in the code, I call it Km for the matrix abbreviated by K. And now I want probabilities. And you can already imagine these are not useful as a probability, because if my drunkard is on cell I now want to read off from, let's say he's on cell 13, I can read off here the probability to go to any other cell. Let's plot it. And we see here, these are the cells where he might like up, and all the cells at the bottom are cells where he's unlikely to go. Problem is, these cells don't sum to 1. But if it's a probability, it should sum to 1, so that the probability of something happening is exactly 100%. So what I should do is divide this by divide each value here by the sum of this. And then I get this. And that's what I've done here. I calculated the row sums of my kernel matrix and divided each row by the row sums. And then I get a matrix of probabilities. And each row in this matrix tells me the probability distribution of where the drunkard will go if he starts at this cell. And that's what I call the transition matrix. And here I was slightly inconsistent in the code. I called it trim for transition matrix. In my formula, I called it P for matrix of probabilities. Sorry about that. So Also keep in mind that we have this vector z, which are the row sums by which we've divided. We will need that later because it will strangely turn up at all kinds of places. So now I can pick some random start cell, like here cell 612, and can look at this value 612 here and take the probabilities there. So here m, halt. So let's take this here. And now what I can now do is I take the 612 cell, this matrix, and now I have here the probability to end up on any other cell. And because this is 1,000 numbers and hard to look at, I visualize it by plotting my curve here and coloring the cells with this by the elements of this matrix. And as you see, most matrix elements are nearly zero, so most cells are nearly black. So here, this is the code. I just take my data matrix, add a column with a probability, so that I get this here. E 612. And here is now the two coordinates on my to-do space and the probability, and that's what I get. And as you can see, it spreads out a little bit, and it really looks like the typical diffusion pattern if you put ink on a tissue. What I can now do is ask what happens if I wait for another step. So here this orange cross, by the way, marks the cell. What happens if I do another step? And if you think about it, one way how I can think is by matrix vector multiplication. I say my initial state is a vector where the brown cut is with 100% probability on cell I. So I can say I make myself a vector which has all zeros except a 1 at one cell. And now I multiply this vector with my matrix. And then this, because I have a basis vector which has a single 1 at one row column, this thing here multiplies, this thing selects out the ith row from P. Usually if you have a matrix vector multiplication, you get the ith column, but here you see I have multiplied from the left, so I get the ith row. That's of course just a matter of convention. I have normalized my P so that the rows add up to 1. This is why I have to multiply my vector from the left. If I had multiplied them that the columns add up to 1, I would have multiplied from the right. The Markov chain people, you know, it's always annoying in matrix algebra that you have to do everything from the right to the left because it's so confusing that if you have matrix A times matrix B times matrix C times vector, that you have to imagine, okay, this is the vector being transformed by C, by B, by A. So you have to read matrix vector multiplication always from the left, which happened because, and the Markov chain people, they decided that's annoying, let's do all our matrices, let's multiply all our vectors from the left to the matrices, and always write it from that you can see the initial vector with everything 0 and the 1 at the cell I goes from the left into the matrix P, and we get out our new matrix 1. Which of course means that technically all these vectors are row vectors, so we have to put a little t. And if I now do this, I multiply this from the left. I write so VOT times P. In R you don't have to transpose the column vector into a row vector, it does that automatically, so I don't have this here. And if I do this, I get exactly the same result than if I looked in this column. But what I can now see is that obviously, if I now take this vector and multiply it again from the left onto the matrix, then I see what happens after 2 steps. Because I have my probability vector, and if I push it once more through the matrix, I get the distribution after 2 steps. Is that obvious to everybody? So we can say the distribution after 2 steps is the distribution after 0 steps times P again, or times P squared. I write it like this here. I don't want to square my matrix yet because this is less calculation than squaring the matrix. And after t steps, I can write it, I have to do with t times, and I can write this formally as taking the matrix to the t square, but probably computationally it's better to push the vector from this and multiply it, because here we always make matrix vector multiplication, while to calculate p to the t, we have to make a matrix-matrix multiplication. So that's what I've done here. You see, ignore this big if block for the moment and just look at the rest. I start again with my vector on position I, with as a basis vector where everything is 0 except for the cell 619 is I, and then I run 300 steps, and in each step I calculate, I multiply the vector with a transition matrix, so that we repeatedly always multiply again and calculate the next step. And if I'm at the 0, first, second, third, fifth, 10th, and so on step, then I'd put in this code here to draw the whole thing. And this is how it looks like. At the 0th step, we have the 1 here, and the rest is 0. At the first step, we have this, what we've already seen. Second step, it has spread out a little bit more. Third step, it has spread out even further. Fifth step, it has spread out quite a bit. So we see this really is able to creep along the manifold, which makes it useful for us in order to see, to understand, to get a pseudo time. After 10 steps, we've crept even a bit further, reached here already the end. After the 20th step, we've also reached here up to here. After the 30th step and so on, 50th, we are already here, and after the 100 steps are here. What you also notice is from the 50 to the 100 steps, something else happens. The majority seems to end up here. And after 300 steps, nearly everything is here. Why did it end here? Because here the points are densest. So here is a high probability of a drunkard just stumbling back and forth between these things because they are also close, so there's a lot of points of high probability. And once you end up here, it's really hard to get out again. And this is a typical thing for a Markov chain. You have what's called a stationary distribution. No matter where you start, after a large number of steps, you will always end up in the same final distribution. Actually, not always, but only under certain conditions. There is a long mathematical theory about how you figure out from the transition matrix whether the Markov chain will end up in one final state. But here in our cases, this is always the case, because first, the two most important prerequisites are the Markov say everything should be connected. So in principle, it should be possible, at least via intermediate steps, to get from any cell to any other cell. That's the case here, but it wouldn't be the case if we had two completely separated blobs, which are so far from each other that the probability is essentially 0 to cross. And the second important thing is our kernel is diffusive. That means it spreads out. You could also construct a transition matrix where, for example, the probability is always 100% to hop to the next cell to the right, when everything would just run in circles round and round and round. But certain kernels are guaranteed to make this, as they say, diffusive. And I don't want to get into this theory. Also, I've forgotten exactly what the definition, what the exact precondition is to make sure that a matrix chain has exactly one limiting stationary distribution where you always converge to, no matter where you find it. But I can guarantee you, for the kind of Markov chains you find with this approach, where we use this Gaussian kernel, this will always be the case. So let's check this first manual whether this is the case. Run a few more. So here I have run 1,000 steps, again starting at the same starting point. And as you can see, we end up at precisely the same as here. So nothing much happens anymore after 300 steps. And now, how do we find this stationary distribution? There's one thing that we can say. Imagine we would know the stationary distribution pi. Then if we put the stationary distribution pi into our matrix, we should get it back, because after all, it's stationary, it's the limit. So it should be a fixed point. Pi multiplied with t should again be pi. If you look at that, if I get rid of these stupid t's, then I notice this is actually an eigenvalue equation. P of applied to pi gives pi back. So we are looking for the eigenvalue to the eigenvector of eigenvalue 1. Another thing, instead of solving the problem, we do something else. So remember that at the beginning, I told you to keep in mind the vector z. This vector z or z was the row values which we took here. At the very beginning, when we normalized our transition, our kernel matrix to make it probabilities, we said we have to divide each row by its row sum. And I kept here this vector z of the row sums. In this vector z of the row sums, it has a funny property.
Also, it's kind of like reminiscent of the density.
Exactly, it is reminiscent of a density, and it actually is the density. And we can easily see what's happening here. If I take this vector z and multiply it, so this of course written as matrix vector multiplication means I sum over all the columns and have now here the ith components of the probability of the vector z of starting according to the vector z of ending up at cell I. We have to go over all the, isn't there a, we have to go here over all the others, j, multiply this out, but this pij, we got it from our original kernel matrix kij by normalizing with z. And now the normalization that we put in order cancels with the z that we put in, and we get back our original kernel matrix, summing over all of them. And because we sum over all of them, we get back our normalization, and then we're back at z. So that's a bit a strange mathematical thing, but you can imagine exactly as Philip said, because z sort of captures the density, and the density tells us where it is. But this is not roughly true, but because of this, it's exactly true. The other point that we've noticed is, as I've just said, we also notice that it's an eigenvector for the same reason. But but z itself isn't a probability distribution because itself it doesn't we used it to normalize the matrix to 1, but itself it doesn't normalize to 1. So let's quickly fix this and divide z by its own sum of components. So that z now sums up to 1. So the normalization factor is the sum of all its components. I can also say this is the L1 norm if I want to. And now I get a new vector which I call pi. And that's the stationary distribution. I shouldn't call z the stationary distribution because it isn't a distribution, because it isn't probabilities. Pi is. In my code, again, I was a bit inconsistent. I call zv for the unnormalized vector and zn for the normalized vector. But when I changed my mind to call it pi because it's also called pi in Wikipedia and everywhere else. Now let's see if this really works. Take this vector that we've just calculated here when we made this 1,000 steps and compare it with this vector pi, and as you see, they're identical. So, now, and as I also said, we can do an eigendecomposition by taking the eigenvalues, but because we have our strange left eigenvalues, we have to compose it, so because otherwise, because eigen, of course, does the normal column eigenvalues and not the row eigenvalues. And as expected, all the eigenvalues, the largest eigenvalue is 1, and all the others are smaller. That all the others are smaller can be easily proven, but I don't want to show the proof now, but it has something to do with if you go in there with a normalized probability, you have to come out with a normalized probability, and if it had an eigenvalue larger than 1, then you could construct something that isn't that doesn't keep normalization. So we can also see, of course, because this matrix here wasn't symmetric, the eigenfunction did a complex eigendecomposition. The complex this is why we get all the i's. So, and we should actually have expected that the eigenvalues might be complex, but in fact they are all real. Only R didn't know that they will be real, because only if the matrix is symmetric you have a guarantee that it will be real. Why these ones are real, we will see afterwards. For now, let's just see they are actually all real. And the eigenvectors, they are also all real. It doesn't look like that, so here I calculated the argument, so the face value of it, and you see it's either 0 or it's pi or minus pi, so they are all positive or negative, but don't have a component to I. So these are all real. And of course, the first eigenvector is the same as our z, as expected. Not quite the same, because the eigenvectors are normalized to have L2 norm 1, while our Z we normalized it to have L1 norm n. But so the slope is not 1 here. So, and now how do we use this whole thing to define a diffusion distance? We could simply say, okay, in order to define the diffusion distance from I to j, we could simply ask, let's start a random walk at cell I and ask how many steps do we need until we have a sizable probability on cell j. But for that, we would have to decide a threshold and say, okay, when do we get above j? And somehow this all seems to be a bit sketchy. And by trying around the people who came up with this whole diffusion distance, they decided that actually what works better is to do it in a more symmetric fashion. We start a random walk at cell I, and in parallel start another one at j, and then we run them for a fixed amount of steps t, and then we ask how much overlap is there. Because you can imagine, if we run it, for example, for 10 steps, here you see how it looked after 10 steps when we started here, and now imagine we had another one which started here and which had 10 steps, then we would have overlap here, while if we had another one with 10 steps here, then the overlap would be quite small.
I have one question. To me, it's not very obvious why I guess probability of going to another cell always needs to be summed up to 1, because like from what I'm thinking, like some cells aren't very dense, right? And then the cell might not go to any other cell.
It depends on it's not the probability to go to all other cells, to go to any cell. One subtlety that I stepped over, but that's actually important, is here this kernel also has elements in the diagonal, and the diagonal is 0. And so the kernel value for the cell staying where it is. So in contrast to our drunkard on the Galton board, this drunkard has the ability to stay where he is and not move. And the probability to stay where you are is actually the largest, because the distance is shortest. And including this, it has to add up to 1, because of course the drunkard has to end up somewhere. So, using this now, we now define our diffusion distance as follows. We take a cell starting at cell I, so this is again our basis vector with a 1 at I, and run its t steps through the transition matrix, and then we get a probability distribution which I call YIT, which tells us the probability distribution if we start at cell I after t steps. Obviously, because here this EIT simply takes out the ith row of a matrix. This thing here, this vector, is simply the ith row of a matrix P to the t power. And we do the same with the other cell, because we want to get the distance between cell I and j. So we calculate, in a way, we calculate the t power of this transition matrix, and now we compare the ith row and the jth row of P to the t. And if we compare them, we could simply take their Euclidean distance, and say this is my diffusion distance, or the square root of this is my diffusion distance. So I take the ith row and the jth row, and of course I have to add up over all columns, and take here, going from column 1 to the last column, I always take the probability to end up on cell L starting at cell I, and the probability to end up at cell L starting from cell J. I take the differences between these probabilities, square them, and add them up. But as we will later see, it actually turns out to be useful to not simply use these terms as they are, but to weight each term with pi L, the Lth component of a stationary distribution. One intuition why this might be useful is to say, we should consider this difference on the scale of what the typical occupation on this cell is. If a cell is far out and we never get there, and so it has a really low value on pi L, then if we manage to get there both from cell I and cell J, this has more meaning than if it's a highly. But this is a bit a hand-waving argument, especially it wouldn't explain to us why we have square the probability in the numerator and not in the denominator, which confused me quite a lot when I prepared this, but we will see afterwards why this is the case. So, but if we do this, but now let's for the moment just accept that Kaufman and Lafon have said that we should divide each component by this pi L before summing them up, and that therefore, and then we get what they define as the diffusion distance for time t. So you see there's not one diffusion distance, but a family of distances, one for each time. And you can imagine that with diffusion distance, they interrogate different scales. A diffusion distance at time 10 is good to interrogate distances along the scale that we see here, so at the medium distance, while at time 50, it can see rather large scale distances. So we can imagine that if you have a small side branch sticking out somewhere, at a large t, this thing will be completely unapparent, while at a small t, we will see it. So the choice of our times, of a number of time steps, tells us something about how much, how much we want to average over small structures, and how much we want to take a bird's eye view on the whole structure. So, using this, so what we now do is here, in order to write this here conveniently, I take this pi L, pull it under this square here, and write it manually under each of the two. So instead of pt, I take the distance, I take this Th power of the matrix P, and now I divide each element of this Th power by square root of pi L. So instead of using the Pth power of T, I make a new matrix Q, which is the matrix Pt, where each column is divided by the square root of a corresponding stationary probability. So I get here a new matrix Q, which I get out of a matrix Pt by dividing each column by an element of pi, by its square root. And the point is that now I can simply write my diffusion distance as the Euclidean distance of two rows of this matrix Q. And so in order to do this, I now calculate Q explicitly. So I start off by calculating P10 simply by starting off with an identity matrix and multiplying this identity matrix 10 times with P. And then I get P to the 10. And then I take this and define each column by the square root of this pi, which I call Zn. And in this way, I now get a matrix Q. And if I now use the dist function, which I remember gives me a square matrix of the distance, is the Euclidean distance of any row to any other row, I get this matrix Dij here, this matrix D10. So I take this matrix Dgen, and now, of course, I can take again my cell I and say, let's take out the ith value of this cell D10. And now, if I do this, I can, here is, I think my cell mixed. Originally it was up there, but unfortunately I changed the value I in here, so the cell is now down here. And from this, you see, from this cell, we see the diffusion distance at time t to any of the other cells. You see, it works quite well. The diffusion distance increases monotonically if you move along our curve. And for each cell, we can now read out its diffusion distance to all other cells from this matrix D, which is the distance matrix of the rows of Q, which we got from Pt by dividing by the stationary distribution. Now there's two more things I have to show you. One is how I use this diffusion time to solve a branching problem, and the second, how to calculate the diffusion time. Because the way how we've calculated the diffusion time just now is quite annoying. This for loop here is incredibly slow. Here it's only 1,000 cells, and we only want to go up to t equals 10, so it takes maybe 30 seconds. But still, it's not good. It's not good for a couple of reasons. First, if we had, instead of 1,000 cells, we had 10,000 cells, when our square matrix would be 10,000 by 10,000, or 100 times larger, and this for loop would probably take half an hour. And that's not acceptable. So we need a way to calculate this pseudo time without making this for loop. So we have to think how we can more elegantly calculate this p to the t, this t power of a transition matrix. But before I show you how to do that, I want to show you if we now have calculated our diffusion matrices, either using this very slow method here, or the better method that I'll show you in 10 minutes, how can we now use this to get branching? And what I now want to do is I want to find the endpoints of the branches. This point, this point, this point. And the way how I do this is I just take my random cell here and ask which cell is farthest from them. And you can already say the cell which is farthest from all of them is that one. So I take all the distances of my initial random cell I and ask which one is furthest away, and I call this the end cell. And you see, that's this one here, the end cell. Now I ask, what's the distances to the end cell? And here you see the end cell, and the distance, the cells with the highest distance is this one and that one. Now I want to pick this one. And so I ask, what is the high from of all the cells which have a y coordinate which above 0, what is the one which is farthest out here? And I do this, and now I get another cell, this one, now I call this the start cell, and this the end cell. And what I will now do is I plot you the distances of all the cells to the start and end cell. So each point here is a cell. The x-axis is the distance of this cell to the start cell, and the y-axis is the distance to the same cell to the end cell. And you can see what's happening here. This cell, which has distance to the start cell 0, this is the start cell, while this here is the end cell. And these are the cells between start cell and end cell, neatly ordered by pseudotime. In these cells here, that's the third branch which sticks out from that. So this is how I now find branches and pseudotime in an unambiguous way. I have first used diffusion time to define a distance measure between any pair of cells such that the distance is calculated not straight across, but by slow diffusion along the manifold, in always making small steps of the size of a kernel. You remember my kernel was 0.3, so I can never step much more than 0.3, and my diffusion distance hence measures along a line, along many lines, which makes these small steps. And hence the diffusion distance goes along that. And now, once we have this distance matrix, we can identify a pseudotime by just finding the start and the end cell, by just taking cells which are very farthest from all the other cells. And then I look at the distance to the start and the end cells, and this automatically orders my cells. Now I can use this to actually give me a pseudotime by just looking at the difference between start and end cell, because the difference is the distance of a cell to the main diagonal. So here I have a main diagonal, and the distance to the main diagonal, of course, tells me where I am. And that's what I've done here. I calculate the distance for each cell. I calculate the distance to the start cell and to the end cell, take the difference and color by that difference. And now you can see we start here by a -10. Here we have middle and go here to +10. Now again, I see a nice pseudotime which goes. And this pseudotime is a bit different from our previous pseudotime because it depends on density. Where the cells are dense, it progresses slowly, and where the cells are sparse, it progresses faster. Simply because the diffusion smears everything out here and can't distinguish between here and here. And of course, I have here now this thing sticking out. Now this plot here, it shows me how well I can see these branches. Here you see at diffusion time 10, it was quite a good choice in order to see these branch well and clearly say, okay, these are on the main branch and this is the side branch. But we can quickly calculate this also for different pseudotimes. So I run this here for only 1 time step, 2 time steps, 3, 5, and 10. And you see from 5 onwards it becomes useful. After 20 or so, we get this, what I've said before, where we sort of average over the thing, because at 30 or 100 steps, we have enough time to just step in here and step out without losing much time. Hence, you can use this kind of plot in order to decide what kind of pseudotime to use. And then we see 10 was actually a good choice. So, questions about this so far? Then, sort of to finish our term with some complicated bang, we do some real math now to see how we can efficiently calculate the powers of this pseudotime. And when the main way how you calculate powers of matrices is eigendecomposition. Why is that? Is that the case? Because imagine you have a symmetric matrix S. And because the matrix is symmetric, it has a real eigendecomposition. You can write as U lambda U transpose. What happens now if I take S to the 5th? You have U lambda U transpose. First S, U lambda U transpose. Second S, and you see here, we always get next to each other U transpose and U. And they cancel, because UTU is the identity, because this is an orthonormal matrix. That's the point of an eigenvalue decomposition, to have something which is the inverse of each other on both ends. So we get U lambda to the T UT, which is actually, or in my case, lambda to the 5. So in order to exponentiate a symmetric matrix, you just get its eigendecomposition, and then you just exponentiate the lambda. Because the crucial point is the lambda is easy to exponentiate. It's a diagonal matrix. If you multiply a diagonal matrix with itself, each diagonal simply multiplies with itself. So this here, lambda to the 5, is simply the diagonal matrix lambda, with each element on the diagonal taken to the 5th power. So, in other words, S to the 5 is the matrix which has the same eigenvectors as S, but all the eigenvalues taken to the 5th power. And this is one of the reasons why eigendecomposition is so important, because it allows us to take matrices to the power. It's also the other way around. It shows us how eigenvectors are actually calculated, because so far we always use this eigenthing or the Irlbar thing. But we can do the other stuff in order to calculate an eigendecomposition. You put a matrix in. You have a matrix and you multiply a random vector with this matrix and do this repeatedly, as we've just done before, where we calculated p to the t times some vector. So if I were to calculate s to some power t, what I can then do is I don't have the eigendecomposition. What I can do is that I say, what happens if I apply the t power of my matrix S to a vector V? And let's assume this is a random vector V, which can be decomposed in the eigen, let's say, UI, rho I, UI. So because the U's form an orthonormal basis, I can develop the vector V in this orthonormal basis, getting certain coordinates rho. And so rho are the coordinates of the vector V in the eigenbasis. Now what happens now? Because U is an eigenvector of S, we can already see that this then gives us some rho I, ui, lambda I to the t. Why that? Because ui is an eigenvalue of s to the t, with the ui is an eigenvector of s to the t, with the eigenvalue lambda I to the t. Because we just said if we exponentiate, if we take a matrix to the power, the eigenvectors stay the same, but the eigenvalues go to the t-th power. So now our new vector, our resulting vector, has still the same components, but each component has now been multiplied by lambda I to the t. Now let's imagine we normalize this vector afterwards. STV over, when this thing is already normalized, then we have to say this is rho I lambda I to the t ui, and here we have the same without the ui. And you can imagine what is the sum here. It is completely dominated by the largest eigenvalue, because if one eigenvalue is 10 and the second highest eigenvalue is 9, then of course 10 to the 10 is much larger than 9 to the 10. And we can now, and I don't want to spend time on this, but what essentially happens is the basis component that belongs to the eigenvector with the highest eigenvalue will be multiplied with the largest value, which means that the vector is turned towards the top eigenvector. And there you can see how you can find a top eigenvector of a matrix. You start with a random matrix, keep putting this vector into the random matrix, multiplying it with the matrix, multiplying it again, the result again onto the matrix, and again, and again. And every time the component aligning with the highest eigenvector will be boosted more than the others, so the vector will be slowly projected onto the highest eigenvector, and at some point the vector will hardly change direction anymore, and then you know the vector points into the direction of the highest eigenvector. To show this, one would now usually, we would now take this thing. I don't want to write this on a board now because I'm getting wrong, but if you think you're missing something in math, it's called the power method, and you find it in Wikipedia. The catch of the power method is that it isn't numerically stable, and all these many different eigenvector methods, like the Irlbar that we always went, and the different variation of the Landros and Arnoldi and whatever iterations, they are all different tricks to try to make this power method stable. But yes, so this is about taking a matrix to the power. And now I've told you how to take a symmetric matrix to the power, but unfortunately our P isn't symmetric. We started with a symmetric matrix, K, the kernel matrix, but then we made it non-symmetric by making the rows add to 1. And now comes we make a funny detour. We make it symmetric again, but slightly different than it was before. And then we suddenly notice that it still works. So, and what we do here is, so the first thing is, we remember that we wrote, so I think I will now, that what we did is we divided K row-wise by Z. We divided each row of the kernel matrix K by an element of this normalization vector Z. Now, one way is if you want to divide each row of a matrix by an element of a vector, one way how you can write this is by taking by making a diagonal matrix where the row is on the left hand and where I just write it down. So what we want to do is we have divide each row of P of K, so that's the symmetric kernel matrix, by an element of Z. And with Z, just to remember that, we said this is the same as our stationary distribution pi, but not yet normalized. So this is this normalization constant. When we said we changed Z into pi, we have defined, so Z is the row sums of K, and zeta is the sum of Z, and pi is then the normalized stationary distribution. And the way how we can do this, how we can write this, is that we say P is 1 over zeta pi to the minus 1k, where so you see, we take the vector the vector pi, and I turn this vector into a matrix by making it a diagonal matrix where the diagonal is the vector pi. The point why I do this is multiplying a diagonal matrix with a vector, with another matrix, is the same as dividing each row of that matrix by an element from this diagonal. Again, if you think about the column times row, you can see that this ends up. If this is diagonal, then each element. Now on the diagonal, I don't want to have the elements of pi, but I want to have the elements of 1 over z, so 1 over pi and 1 over zeta. That's why I put this minus 1 here. The reason why I rewrite this as a diagonal matrix, because it makes our whole matrix thinking easier. So what I do next is, I now, so this thing is symmetric, but this thing is not. Actually, I should probably record the board in case somebody wants to look at that. So, why is there strange stuff at the bottom? Where is my thing here so that I can cheat a bit? So I do this, and now I define my matrix S, which is the same as this one, but this time, so I keep this as it is, but this time I don't normalize K by dividing each row by an element of pi, but I divide each row just by a square root of that, and the other square root I put on the other half. I show you how this looks in our code. In our code, this actually looks like this here. I first take the rows and divide them by the square root, then I transpose it, and then I take the columns and divide by the square roots. And the upshot is this matrix is now symmetric. And it's sort of half normalized. We can't use it as transition matrix anymore because it's not a stochastic matrix. Its rows don't sum up to 1. But it's similar to it. And the reason why this is useful is, let's first get our eigenvalue decomposition for this thing. We can also, for later record, it's also related to P, of course. If I define this here now and I put this, well, you've seen it up here, it's P to the 1/2 times P times pi to the minus 1/2. So, and this thing now has an eigendecomposition. U lambda, I will need this up there. So I now ask, if this is K, what is P? So I invert this matrix, say, okay, P times pi is K, and if I put this for this K, and then what I will get is that the zetas cancel, and this pi to the minus 1/2 gets multiplied by the pi to the up here and becomes a pi to the plus 1/2. P pi to the minus 1/2. So, and now we get the eigendecomposition of this thing. U lambda U transpose. And as you can now see, I can now write P is pi to the, let's turn this around. We take our P, say this is pi to the minus 1/2, S pi to the 1/2. So that is this equation turned around. And now I put in for S the eigendecomposition, P to the minus 1/2 U lambda ut P to the 1/2. And now something magic happens. Because if I now calculate the transition power of this here, then I get this is P to the minus 1/2 U lambda ut pi to the 1/2. And now comes the next U, the next P. And it's again P to the minus 1/2 U lambda ut P to the 1/2. And you see the magic still works, because here we have a P to the 1/2 and here we have a pi to the minus 1/2. This is a diagonal, this is a diagonal. And their elements are reciprocal to each other. So these two cancel. If they cancel, then these two end up next to each other and they also cancel. So I can strike out this and then I can strike out that. And then I'm just left with pi to the minus 1/2 U lambda to the t ut pi to the 1/2. So even though the matrix P wasn't symmetric, we then can still use our exponentiation trick. And the only issue that we have is that we have these P matrices, these pi matrices around, but they are sitting at the very outside. So they will not hurt us. We only, and that's the difficult part, which actually took me quite a while, have to make sure that we keep well track of where the minus and where the plus is.
But is there no, is there no typo for like S equals digital because how is the like the first part different from the second with the pi to the power minus 1/2 and then again pi to the power minus?
So look at the first part. Okay, I can show you here. So here, this is how I define S. In P, when I did calculate the transition matrix, I multiplied the normalization matrix from the left to the kernel matrix. Now I decide that I make a new definition where I multiply only one part of the matrix from the left and the other part from the right. So instead of having the full pi, I only have the square root of pi here, and the other square root of pi I put here. That's so far just a definition, which is bound to give me a square matrix, a symmetric matrix. Now I wonder how I can use S in terms of P. So what I have to do is I take here the definition and change it around to get what K is. K is zeta times pi times P. K is zeta times pi times P. The zeta cancels with zeta, the pi changes this, multiplies with this pi to a minus 1/2 and makes it to a pi of plus 1/2. So, and that's how this now happens. And now we have here the symmetric matrix with these p's. And what I then do next is I put the pi to the 1/2 and the pi to the minus 1/2 over there to get an expression for p. And now they sort of straddle the eigendecomposition. And now I can take p to the power, because if I take to the power, then always this pi to a 1/2 and this pi to a minus 1/2 will end up next to each other. They cancel, so that then the u and the ut will next to each other and also cancel, and we get that we can just again simply exponentiate only the eigenvalues lambda, and have the u's and ut's around it and the pi's at the very outside. So we are slowly getting to 1, so I have to probably skip this a bit that you can read it at your leisure at some point. Oh no, now we're losing. Ach nee. This thing drives me nuts. If I turn it around. So anybody has another adapter, or maybe for instance for change this one here works? Okay, let's try here. So what I can now do is, so I've tried this out here, so I write this all in R. I first get S, which, as I said, is kernel matrix divided by 1 square root of our normalization vector for the columns and 1 for the rows. And I've pulled the zeta around so that I can do this better. Then I do the eigendecomposition of my new symmetric matrix. And now I have lambda and I have U. And what I now do is I define two things. I call this part here I call psi, and this part here I call phi t. So that I can write the whole thing as psi lambda to the t phi transpose. And I make these two matrices. So again, these are just U with the eigenvectors, and now I have to multiply the rows with these pi's here. And now I can calculate something like this here, psi lambda to the t phi t. And I can now do this much easier by simply saying psi times the diagonal of the eigenvalues times phi. And I can calculate with, compare this with what I've calculated earlier, and you will find that they are the same. But, and now comes the crucial trick here. Let's look at this middle term here, these eigenvalues. We put eigenvalues to the 10th power, and we've just already talked about earlier with power method that these eigenvalues have the thing that, of course, if you take them to the 10th power, that has much more effect on the high eigenvalues than on the low ones. So, if I now were to, let me go here and diff this up to, so if I look at the original eigenvalues, they are actually quite, let's run through here quickly. That might take a moment. Now it runs here with 1,000 things, which is completely super. Here I have now my I left. Okay, what I'm heading at is the eigenvalues, they are all quite large, but they're all below 1, except for the very first eigenvalue, that one is 1. So what I now have is diffusion components. I just want to quickly get here trim 10, D10, where is it, and selves. We observe, here's the eigendecomposition. I just need to quickly run this here. SM, Ix. So let's look at this here. Plot Ix dollar values. And as you can see, the eigenvalues, only the first 100 or so eigenvalues are important, and the rest is 0. And if I put this to the 10th power, then it's only the first 10 which are important, and the rest becomes really low. And that means if I want to calculate this stuff here, I don't need the full eigensystem. It's completely sufficient to only calculate the first 10 eigenvalues, because the rest will be nearly 0 anyway when I take it to the 10th power. Consequently, if I have here only the first 10 elements, then I also need only the first 10 columns of psi and phi. So remember, with psi and phi, I get it out of the eigenvectors by dividing or multiplying with z. So what happens here is that in our eigensystem, we can, we don't need the full eigensystem. It's completely sufficient to only take the first 10, 20 eigenvalues and corresponding eigenvectors. And then I want to take my transition matrix to the 10th power. I can calculate this quite efficiently by only taking the first 10 elements. So that's what I've shown you here, where I said, okay, let's only take the first 13 eigenvectors and eigenvalues of this thing and compare with the manually calculated matrix of a full thing. And you see the result of the full transition matrix to the 10th power and this truncated with only 13 values is quite low. But still, so we're nearly the same. But we still have one issue. With full transition matrix, it's an n by n matrix. And if we have 100,000 cells, then n by n is too large in our memory. Now here it looks a bit like, if we only need 20, this here, this psi is an n by n matrix, but only the first 20 or so columns are interesting, the rest is unimportant because it gets put to 0 anyway by this lambda. So it's completely sufficient to only take the first 20 columns of psi. So it should be possible to not work with an n by n matrix, but only with an n by 20 matrix. And that we can do. This is an n by 20 matrix. If we put the rest to 0, this as well. And when we get here an n by 20 matrix, but this thing pulls us back to the whole n by n thing. So the crucial idea behind diffusion webs is let's only take the front part. So in a way, we're coming in with our matrix, with our vector z, and multiply it with psi, with lambda to the t, and then we don't transform back. So we stay in the space into which this is, because as you can see, what's happening here, there's some scaling dividing each vector component by square root of z. And then we just rotate the bases into some bases where only the first couple of components are important, as we know it from a PCA. And this here, this scaling the vector by the square root of it is something we've seen before. Namely here, when we've looked at this Q and that we define this matrix Q where we divide each element of P to a T by square root of pi. And this is precisely what's now happening here. We can say that if we remove this last part, we just take P to the T, we just take psi, lambda, what have I done here now? That was what I wanted. I've written it up in the other way around, so I explain it now differently. So from now on, we will calculate only psi times lambda t. So we take some vector, some initial vector ei, put it at psi and at lambda to the t, which gives us the ith row of that thing. And these things, this we call the matrix W. And this matrix W allows us to calculate Euclidean distance between the rows of W and use them as the diffusion distances. On the first hand, you would say, no, but this won't give us the right diffusion distances because we haven't transformed back by phi. But phi does exactly this division by square root of pi k that we wanted. And this is now the real reason why we divide by square root of pi k. Not in order to account that it's denser, but in order to justify not multiplying with this phi, because that makes the math difficult. If we don't multiply with this phi, we make an error, which is exactly this dividing by psi k, and then we can write our whole thing as these matrices W, of which only the first few columns are interesting, because the later columns are all put to 0 by the low values here. And what we then have is we can do this here. This is now how we do this quickly. We calculate our symmetrized matrix, calculate the eigenvectors, not all of them, but only the first 15 or so, calculate our psi from that, multiply this with the eigenvector to the 10th to have this psi times lambda, which gives us the W. And now we have this W, and for each cell we have now a vector like this, which goes down and down and down, and from the 15th onwards, the components are so small as we want. And if we now take the difference between two columns here, this is more or less the same as if we calculate the distance manually using our original calculation. And this is that fast because it just does one eigenvector calculation of first and the rest. So we can make one little function which takes our original kernel and immediately runs through in one thing and gives us this stuff here. And yeah, and now that we have this way to quickly calculate one to everything, we can also redo our calculation here. We can ask how much difference did it make that we now use, that we now truncated this, but we get more or less exactly the same values. Now it's already past 12, but if you want to, you can look at the rest. The remaining stuff that people would do is that when they say, as I said in the beginning, let's not write the full kernel matrix. Let's only write the kernel matrix over the 20 nearest neighbor and put the rest to 0 to save some time. Then we can also have a sparse matrix, which is smaller, and we can get our eigenvalues quicker. But because we are missing a couple of neighbors for the small components, the diffusion times distances become a bit larger until it catches up. And we can do our usual game of saying sigma, the kernel should not be as wide or small as it should always depend on how dense it is at that point. And here again, our references, this whole diffusion map idea is by Lafont and Kaufman, and then there is some biology stuff where we try it out for biology. But I find this math so elegant that in the end, you run through the thing and then you notice, actually, you have to calculate for each cell only sort of a 20-dimensional vector, and then you can calculate each cell to every else and get the diffusion time. And if you want to recalculate the number of t, you just have to recalculate which part, which is only diagonal. So, the end was a bit rushed, sorry, but we got to a nice end. And I hope you got a feeling of how this kind of math works that you use for single cell sequencing and how this feels to work in that. So, yep, with this we end our term. Hope you liked it. And we should probably, if any of you have some interest in what else we can do, what kind of lecture we can go in, I now have to plan about what will be the next lectures that I give in the next term, so I'm open to suggestions. And if you have any summer students, please let me know. Otherwise, see you around.